Hello viewers, you are welcome to the second video on the necessary and sufficient conditions for Laplace transform. In the first video, we consider what is called a removable discontinuity, that it's possible for a function to have a point of discontinuity, and there are certain conditions that could actually make us to remove that point. And we call that one removable discontinuity. And that is a very important condition before we can solve any, provide the Laplace transform of any functions. Okay, so in this video now we are going to consider another point which is very important, and that one is called piecewise continuous. Okay, but before we proceed, always remember this definition of a continuous function, okay, which we are going to consider in this video, because we want to consider another aspect of continuous function, okay, at a point. But this time around we are now going to consider what is called piecewise continuous. Okay, so let's consider this function f of t. But the point is this function piecewise continuous? Looking at this function very well, we can easily discover that there's a point of discontinuity there. Yes, look at it very well. Look at it. Okay, when the function is between 0 and 2, the function is t, okay? And when the function is exactly at 2, the function is equals to 4. Now, if you look at this function at t equals to 2, look at the first one, you will see that it is less than 2. Less than 2, that's for instance 1.99999. So in the first part of the function, it does not contain 2. But the second part, it is exactly at 2, which is 4. Now, this is telling us that something is happening there. At t equals to 2, something is indeed happening. But we are not to judge by that. Let's try to plot the graph. Looking at the graph now, we can see now that within 0 and 2, the function is actually increasing, and it is like this. But exactly at 2, the function is 4. That's why I can see the red cross at the top there. And at the same time, immediately after 2 to 5, the function is 5 minus t. But the point is this function is continuous. But what happened at 2? So what happened at 2 is to tell us that at 2, the function is discontinuous at 2. But before we proceed, let's take a time to look at this continuity of a function. A function f of t is actually said to be continuous at a point c, if and only if f of c is divine, and then the limit of this particular function at t tends to c is equal to f of c. Now, if you now look at this very well, now back to the problem, you will now say that indeed, as the function is tending to 2, the function is indeed 2. But from the right hand side limit, the function is actually tending to another thing, which is 3. But exactly at 2, the function is 4, which is an indicator that the function is discontinuous, because it does not satisfy this particular condition here. It does not, because we can see now that at 2, as the limit as x is tending to 2 from 0, from 0 to 1, 1.5, 1.3 up to 2, the function is tending to 2. And if you look at it from the other side, it is from 5 to 4 to 3 to 2.5, 2.4, 2.1. The function is tending to 3. And exactly at 2, the function is 4. That is a very good indicator that the function is discontinuous at exactly 2. So before we leave this slide down, we need to call our attention to the fact that this particular function f of t is indeed divine at all points between 0 and 5. Although that definition, it has some conditions at 2. But the fact is that the function is divine between 0 and 5. And another thing is that this function is divided into 3 sub-intervals. The first interval between 0 and 2, the second interval at 2, the third interval between 2 and 5. And what happens there is distinct. So we can now come back with the fact that between 0 and 2, the function of t, which is equal to t, is continuous. Okay. Another thing we need to notice about the function f of t, most especially at that point t equals to 2, which we've discovered that there exists a point of discontinuity there, is that if you look at the left-hand limit in the sense that as t tends to 2 from the negative side, let me say it again, as t tends to 2 from the negative side, if you look at that arrow, the arrow that is blue in color, you will get the point very well. Now look at that arrow, the arrow that is blue in color. Okay, if you see that arrow, you will see that the arrow is tending to 2 as t is tending to 2 from the negative sides. Okay, and if you look at the red arrow, the red arrow is for the right hand limit in the sense that as t tends to 2 from the positive angle, from the positive side, that means that from 5 to 4 to 3, t, the function f of t is actually tending to 3. Okay, but at 2 the value is 4. So what does it mean? It means that indeed the limit exists, and then they are finite, because the left hand limit is 2 while the right hand limit is what? Is 3. But at 2 the function is 4. So this is an indicator that there's a point of discontinuity there, and we can actually remove this particular point of discontinuity. The third point now is that between 2 and 5, that means when 2 less than t less than or equals to 5, the function f of t, which is 5 minus t, is actually continuous at that point too. So based on this, we can see clearly that f of t is a piecewise continuous function. Yes, we can say that. We can say that f of t is a piecewise continuous function because it is continuous on subintervals. The first interval, it is continuous. The third interval, it is continuous. Even the middle, which is at t equals to 2, which it was very obvious that it is discontinuous. We can see that that discontinuity is something we can remove. We can remove it because it has a finite one-sided limit at t equals to 2. So based on these conditions, we can say that the function f of t is piecewise continuous on the interval of 0 and 5. Thank you very much for watching this video. So let's proceed to the next one. Thank you.